Okay, good morning, guys. Assalamu alaikum. Welcome back to Inspired Teens Grade 11 Physics/Chemistry. Okay, in today's lesson, we'll be doing energy and change. Okay, and if we can complete this in its entirety in this lesson, then we can start our basics of acids and bases. Okay, this section is not too hectic, right? It's pretty simple. Okay, and it's just some calculations, but mostly conceptual. Okay, just concepts that we need to know. Okay, any sort of calculations we'll discuss, but yeah, it's mostly theoretical. Okay, grade 11 energy and change. So the first thing we can discuss is energy change itself. Okay, so the energy change that takes place occurs because of bonds being broken and new bonds being formed. Okay, when bonds are broken, energy is absorbed from the environment. When bonds are formed, energy is released into the environment. The net energy change will determine if the reaction is endo or exothermic. Okay, so this we have something called an energy change. Okay, okay. Just before I continue, please, if there are any issues, okay, with regards to the connection, then please do let me know and I can try and sort it out. That is, you need to be able to hear me clearly, number one, and number two, the screen needs to be sharing properly. Okay, if it's a bit unclear, as long as it's legible, that's the main thing. Okay, so please don't hesitate to let me know if there's an issue so I can try and sort it out. Okay, but yes, let's continue. So yes, we have this concept of an energy change, okay, that occurs whenever bonds need to break and whenever bonds need to form, which you can imagine happens quite a bit. Okay, then this next two sentences are very important. When bonds are broken, energy is absorbed. When bonds are broken, energy is absorbed from the environment, and when bonds are formed, energy is released into the environment. Now, when energy is absorbed, this is known as an endothermic reaction. And when energy is released, this is known as an exothermic reaction. Okay, and yes, it says the net change will determine if the reaction is endothermic or exothermic. Okay, so essentially, at times you may have energy being absorbed. You will have energy being absorbed and energy being released. Okay, so let's not label each as endo and exothermic just yet, because when more energy is absorbed, that's when it will be endothermic, and when more energy is released, that's when it will be exothermic. Okay, let's look at activation energy. Activation energy, it states, in order to start a reaction, energy first needs to be absorbed to break the bonds. This energy is known as activation energy, the minimum energy required to start a chemical reaction. Once the bonds have been broken, the atoms in the chemical system form an activated complex, a temporary transition state between the reactants and the products. Okay, we'll discuss that when we do the graph, all right? But for now, let's look at a little chemical reaction. 2A plus B gives us 3C plus 2D. Okay, now in order for this chemical reaction to occur, we have to break the bonds of A and B, okay, to form the bonds of C and D. So we have to break these bonds to form these bonds. Okay, so you can see that there is, because when bonds are broken, energy is absorbed, and when bonds are formed, energy is released. There's going to be, there's going to be, the voice is lagging. Okay, that was now. Okay, let's try something different. Give me 1 second, please. More like 2 minutes. Okay, I'm just going to try and fix it. Just give me a few minutes, so 1 or 2 minutes, please. Okay, we should be back up and running. Let me just share my screen and then we can continue. Whenever, okay, let me. Okay, whenever the screen does share, please do confirm that that you guys can hear me. Okay, is this better? Are we back up? Can you guys hear me? Can you guys see my screen? Is it clear? Okay, should be back up and running. Yeah, okay. If there's any issues further, please don't hesitate to let me know. I'll fix them. Okay, so yes, we were discussing, I don't know, I'm not sure exactly what you guys missed, but essentially, in a reaction, there's going to be a certain amount of energy that is going to be absorbed because bonds need to be broken, and there is going to be a certain amount of energy that is going to be released because bonds need to form. Okay, if the energy absorbed, okay, is greater than the energy released, this is an endothermic reaction. Okay, more energy is absorbed than released. That is an endothermic reaction. However, if we have more energy released than absorbed, this is what we call okay. Sorry about that once again. Yeah, just constant connectivity issues. I really do apologize. Let's give this one more go. Okay. And let's try for us to get a consistent, constant connection. And then I want you guys to just tell me, just confirm if you can still sharing, but when it does share, if you can see it and if you can hear me clearly. Okay, can you guys hear me clearly? Like, is it lagging or anything? Hmm. And the thing is that the YouTube link is not working, so I can't even confirm that I'm clear, unfortunately. Okay, just one more time. Sorry, I know I've asked you guys like 6 million times. Can you guys hear me clearly? And is my screen sharing? Okay, I'm gonna wait for the confirmation, but I'm not gonna wait, I'm just gonna continue. Okay, so I said that in every reaction, perfect, thank you, we will have a certain amount of energy absorbed and a certain amount of energy released. That is because bonds need to be broken and bonds need to be formed. Okay, in order to form products, you need to break the bonds of the reactants, okay, to form the products. Okay, so therefore, in a chemical reaction, we can have energy absorbed. At the same time, we can have energy released. Okay, so how do we determine whether something is endo or exothermic? So if the energy absorbed is more than the energy released, that's when we that's when we would refer to it as endothermic. And when the energy released is more than the energy absorbed, that's when we could refer to it as endothermic, and we will do both of those in the graph. Okay, activation energy, that is the minimum energy required for reaction to occur, essentially. Okay, it says energy first needs to be absorbed to break the bonds. This energy is known as the activation energy. So yes, the initial energy that is required, this is energy and change. The initial energy that is required, okay, to start up the reaction. The initial energy that is required to start up the reaction, okay? And the starting of the reaction means to break the bonds of the reactants, okay? Because if we want to form the products, right, if we want to take these reactants that we have and use them to form products, we have to break the bonds of the reactants in order to form the products, okay? And that energy, that initial energy that is required in order to break the bonds of the reactants, okay, is known as the activation energy. It is sort of the energy that activates the reaction, if we want to put it that way. Okay, so yes, let's just look at the difference between exo and endothermic theoretically, and then we can look at the graph. Okay, sure, no problem. I'll do it when I do the graph, because we will need to do it anyway. Okay, so exothermic. Let's have a look at some points about exothermic reaction. So the definition of an exothermic reaction is a reaction that releases heat energy into the environment. Okay, when we think of exo, okay, compared to endo, when I think of exo personally, I think of the word exo. I think of Exo Boost from Advanced Warfare, if any of you have ever played that, but never mind, that's irrelevant. Okay, but whenever I think of exo, I think of something being released. Okay, so exothermic, the reaction that releases heat into the environment. Okay, more energy is released than absorbed. That's the key concept. So we know that they could be energy released and absorbed at the same time. But what distinguishes an exothermic reaction is that there would be more energy released than absorbed. Okay. Second point, net energy change is the energy released into the environment. Okay. Then we have the chemical system's energy decreases. Delta H is less than 0. We'll discuss enthalpy as well after the graph. And the environment's energy increases because there is energy, there is heat being released into the environment. Okay, and the temperature of the environment increases, the test tube gets hotter. Let's have a look at some points for endothermic. An endothermic reaction is opposite to exo. Okay, an endothermic reaction is a reaction that absorbs heat energy from the surroundings. Okay, so an endothermic reaction requires the energy. Okay, it uses up energy from the environment. It absorbs the energy from the environment. The net energy change is energy absorbed from the environment. Okay, sorry, I missed one. There's more energy absorbed than released. That's the key point, right? That distinguishes an endo from an exo. There's more energy absorbed than actually released. And the net energy change is the energy absorbed from the environment. And the chemical energy increases, sorry, the chemical system's energy increases, delta H is greater than 0. We'll go through that in a bit detail in the next part. Okay, and the environment's energy decreases. That makes sense because we took heat from the environment. So since we took heat from the environment, we took the energy from the environment as well. So the environment, the area around the reaction, okay, the energy there would decrease. Okay, then it says the temperature of the environment decreases as well, because that's what an endothermic reaction does. It absorbs the energy from the environment. Okay, so each point discusses very similar thing, but the main point is highlighted. Okay, now let's have a look at this fancy graph. Okay, there's a lot of arrows, okay, but it's not going to be that intricate. We're going to do it for exothermic and endothermic, right? These are what? These are potential energy versus course of reaction graph, or as the reaction takes place, essentially, right? That's why we say the course of the reaction. Now, potential energy versus course of reaction graph. So now there's a lot of lines, okay, but the main reaction, okay, is this here. Let me just highlight it so that we can see it clearly. This is the this is the line for the reaction. This is the line for the potential energy, as how we can see how the potential energy is changing, right? Potential energy on the y-axis. We can see how the potential energy is changing, okay, as the reaction occurs. Oops. Okay, so the first thing that we're going to discuss, let's actually get rid of most of these things. We can always redraw them. Okay, the first thing we're going to discuss here is on the left-hand side, okay, the straight line on the left-hand side represents the reactants. This represents the reactants, the energy of the reactants, because initially, before the reaction occurs, we have reactants. And at the end, we have products. Okay, so initially we have reactants, and at the end we have products, and it's the same thing for the endothermic, right? We'll discuss that. So that kind of makes sense, right? Because at first we have reactants, then we have products. Now, remember the y-axis reads what? The y-axis reads potential energy. So this value from the bottom all the way up to this line of reactants actually gives us what? Something that makes sense. The energy of reactants. The energy of reactants. All right, that gives us the energy of reactants. And of course, from here, from the bottom to this line, that gives us the energy of the products. Okay, that's the first thing. Right. Now, the second thing, we need to understand what's going on with this line, okay, with this curve of this graph. We have an initial energy for the reactants. And then the energy increases until it gets to this maximum point, and then it decreases all the way down to the products. Okay, so firstly, this point here is the highest energy point on top, and it is known as the activated complex. It is known as the activated complex. It is the highest energy point in this chemical reaction. So again, course of reaction. So this is representing the potential energy as the reaction is taking place. So this activated complex is the highest energy point in the reaction. It is known as the activated complex. And I like to talk about the activated complex as a highly unstable, high energy, transitionary state during which bonds are being broken and formed. Okay. At this point, we neither have reactants nor products. At this point, we cannot define what we have as a reactant, nor can we define it as a product. It is it's a transitionary state. It is the point at which we are transitioning, we are changing from reactants to products. Highly unstable, high energy state, okay, where bonds are being broken. Bonds of what are being broken? The bonds of the reactants are being broken, and the bonds of the products are being formed. Okay, so at that point, we're not the reactant, but we're not the product. Okay, but we are in that transitionary state where we are changing from a reactant to a product, and that is known as the activated complex. Okay, now activated complex essentially represents the reaction taking place. So to get from reactants to activated complex, we need a certain amount of energy, right? To get from reactants to the activated complex, we need a certain amount of energy. And that is known as the activation energy. Hmm. Okay, no, it does, it's fine. Okay, that is known as the activation energy. To get from the reactants to the activated complex is the activation energy. So let's define, as someone asked, activation energy again. Activation energy, it states here, in order to start a chemical reaction, energy first needs to be absorbed to break the bonds of the reactants. This energy is known as activation energy, or the minimum energy required to start a chemical reaction. And like I said, that's exactly what activation energy is. It is the amount of energy that we use in order to start up a chemical reaction. So you have your reactants, right? You have your reactants just chilling there, right, in your chemical lab. Okay, nothing's going to happen to them if there's no change in energy, right? If you have reactants just chilling in a closed container, then nothing's going to happen to them. Okay, until we have a change of energy, okay, or it receives energy in order to break those bonds, right? That's only when the chemical reaction will occur, right? So again, in order for chemical reaction to occur, we need to achieve activation energy. It is the minimum, the least amount of energy required in order to start a chemical reaction. So it is essentially the energy needed to break the bonds of the reactants. Okay, that is the minimum energy. The minimum energy that you need to start a chemical reaction is the energy required to break the bonds of the reactants. Okay, also known as activation energy. And it can be seen in this graph when we want to go from reactants, okay, all the way to the reaction starting. That would be the activation energy. Okay, so to go from the reactants to the activated complex is the activation, represents the activation energy. Okay, what can we discuss next? We can discuss a line all the way from the bottom up to activation and activated complex, right? Don't confuse, maybe perhaps many students might confuse this pink line as activation energy, but as you can see that this line represents from the bottom all the way to the top. It's not from reactants to activated complex, it's from the bottom all the way to the activated complex, and this here would be the energy of the activated complex. Energy of activated complex. It's not the activation energy. The activation energy is from the reactants to the activated complex. And from the bottom, measuring from 0, okay, all the way up to the activated complex, that is known as the energy of the activated complex. It is known as the energy of the activated complex. Okay. Now we can discuss the other concepts of energy released and energy absorbed. Now, the energy absorbed is actually the same as the activation energy. It is from, let's throw it next to it. It is from the, what do we call this? The reactants to the activated complex. This is the energy released. Sorry, the energy absorbed. Energy absorbed. Okay, that makes perfect sense. Energy absorbed is the amount of, remember we discussed, when bonds are broken, energy is absorbed. Okay, so we are trying to break the bonds of the reactants to get to activated complex. So all that time, energy is being absorbed from the environment. And as you can see, that the energy of the system is increasing, right? Because we are absorbing energy from the outside. We are absorbing energy from the outside so that we can allow for this reaction to occur. So the activation energy is the same as the energy absorbed, right? Or the energy used to break up the bonds, right? Because remember, we learned when bonds are broken, the energy is absorbed. Okay, so that's important to note. Then we have this change, right? Now, all the way from, we get to activated complex, right? We start off energy of reactants, increase energy to get to activated complex. Then we drop all the way down to products in this case, right? So we go from the top all the way to the bottom. And that from the top all the way to the bottom, that is known as the energy released. That is known as the energy released. So remember, we have in a chemical reaction, energy absorbed and energy released. Okay, because to break bonds, you need to absorb energy, and to form bonds, you need to release energy. So that's why now, remember, we have reactants. We give it its activation energy it needs to get up to the activated complex. Activated complex is that like transitionary state where we're not really a reactant, we're not really a product, we're like in the middle. Then once we pass the activated complex stage, we can now form the bonds of the product. So we are going towards the product until we eventually form the product. So that whole time bonds are being formed. So if bonds are being formed, energy is being released. Okay, so this line represents the energy being released. So I think it's safe to say in this graph, right, we have that's the amount of energy absorbed, that's the amount of energy released. So it's safe to say that the energy released, I'm going to represent it by ER. I'm going to put it here. Energy released is greater than the energy absorbed for this particular graph. The energy released is greater than the energy absorbed. We can see that more energy is released. Don't worry about the direction that it's released in. Is more than the energy absorbed. And that tells us more energy released than absorbed is an exothermic graph. So an exothermic reaction. So this is clearly a graph for an exothermic reaction, because we can clearly see that the energy released is more than that is absorbed. So, okay, that tells us it's an exothermic graph. Okay, and the last and final thing that we're going to discuss is this enthalpy, delta H. Delta H is known as enthalpy, okay, or the heat of the reaction. It is known as the heat of the reaction. And we have two possibilities, delta H being less than 0, or delta H being greater than 0. Now, when delta H is less than 0, you should memorize this actually. Delta H is less than 0 for exothermic reactions, okay? But delta H is greater than 0 for endothermic reactions, okay? Always keep that in mind. So in this case, right, okay, so delta H, how do we calculate it? That's what I wanted to say. The way we calculate delta H, okay, is by saying energy of the products minus the energy of the reactants. Energy of the products minus the energy of the reactants. So in this case, we're going to say energy of the products. By the way, I'm not saying energy released and energy absorbed. That's not what we're working with. We're working with energy of the products minus energy of the reactants. So the energy absorbed is less than that of the energy released. However, the energy of the reactants is more than that of the products. Okay, just look at that, right? Discussing different concepts, energy of reactants, energy of products, and energy absorbed and energy released. Those are different things. Okay, so the way that we calculate delta H, the enthalpy, is by saying energy of products minus energy of reactants. Okay, and in this case, we can see that the energy of the products is less than the energy of the reactants. So we're actually going to say smaller number minus bigger number. And that's why we're actually going to get a negative answer. When we say the smaller number minus the bigger number, that results in a negative answer. So that's why delta H is less than 0. Okay, delta H is our enthalpy or heat of reaction. Okay, and it's less than 0 in this case because we always, the set formula for delta H is EP minus ER, energy of products minus energy of reactants. And in this case, the energy of products is less. So we're saying smaller number minus bigger number, we're going to get a negative answer. Okay, and that's why we can see. So it can be represented by the difference also between these two lines, because this is the difference between the energy and the products. Energy of the products is the top one, energy of the reactant is the top one, energy of the product is the bottom one. This gives us delta H. Okay. Cool. So delta H, energy of products minus energy of reactions. And that's how we get a delta H that is less than 0. Okay, I hope that makes sense. Hope that you understand activation energy now. Okay, now let's have a look at this. This is an endothermic graph. So we're just going to mainly, all the same things apply. Okay, but we're just going to discuss the main difference, and that's simple. Here we have, okay, so of course we know that we have reactants here, right? These are our reactants. And these are our products. Let's do this. These are our products. Okay, so to get from, and then of course, here we have what? Here we have our activated complex, right? The activated complex basically means like, okay, now the reaction is, it's going to occur because we've reached the activated complex where it's just basically just before the bonds are being formed. Okay, this is activated complex. Now, in endothermic, right, the main difference is, so we know to get from reactants to activated complex, this is either activation energy or energy that is absorbed. Okay, and then to get from activated complex to the products, this is energy released. Okay, so now in this endothermic graph, it can clearly be seen that the energy absorbed is greater than the energy released. Now, if the energy absorbed is greater than the energy released, that tells us endothermic. So this is certainly an endothermic graph. And delta H is equal to what? EP minus ER, that's a constant formula, always. The energy of the products minus the energy of the reactants. Now, if we have to compare, okay, in this case, the energy of the products is from here to here. This is energy of products. And what are we going to compare to? The energy of the reactants. This is the energy of reactants. Okay, so now we can clearly see that the energy of the products is greater than the energy of the reactants. So when we say energy of products minus energy of the reactants, we're going to get a positive answer. And that shows us that delta H, the enthalpy, the delta H for an endothermic reaction is greater than 0. It's shown on the graph. Okay, so just easier ways to remember it on the graph, right, for exo and endothermic. So all the other labels that I didn't include, they'd be included here as well, like activation energy, and delta H is there. I suppose that's about it, as well as energy of the activated complex. That's from the bottom to activated complex. Okay, so yeah, hope that makes sense, right? If you're a bit confused, I would recommend like rewatching the video of the same explanation, right? Maybe just look at the graphs again, try and understand it for yourself, and then rewatch the same explanation. Okay, now let's have a look at this. We talk about enthalpy and enthalpy change. Okay, so enthalpy is the total amount of stored chemical energy or potential energy of the reactant and the product. Okay, during chemical reactions, energy can be exchanged between the chemical system and the environment, resulting in a change in enthalpy. This change in enthalpy, delta H, represents the heat of the reaction measured in kilojoules per mole. The heat of the reaction is the net change of the chemical potential energy of the system. And all that means is essentially we are comparing the energy absorbed to the energy released, okay, or the energy of the products and the energy of the reactants. Okay, we are comparing the difference between the two, and that would represent the enthalpy. That would represent the overall energy of the chemical system. Okay, so yeah, there we go. That's that. And then again, we discussed activated complex, right, which is a highly unstable, high energy transitionary state during which bonds are broken and bonds are formed. Okay, so always remember that sort of activated complex. But the nothing. It's we don't really have reactants, nor do we have products, right? It's somewhere in the middle. Now let's have a look at this. We have the effect of a catalyst. Okay, let's read this definition. A catalyst. In order for a reaction to occur, enough energy has to be provided. Activation energy for particles to collide effectively. In order for a reaction to occur, enough energy has to be provided for particles to collide effectively. So this is known as the activation energy, actually, right? We know this. In order for the reaction to occur, we have to have enough energy. Okay, we have to have enough energy. And here they gave you the reason, because we need particles to collide effectively. The more energy you have, the more particles will collide, and the more they'll collide effectively. Okay, so more energy means we need enough energy for the reaction to occur. And that's exactly, like I said, what activation energy is. Activation energy is that amount of energy that you need in order for the reaction to occur. Okay, let's look at the second paragraph. The amount of required energy can be decreased by using a catalyst. A catalyst is a chemical substance that lowers the activation energy required without taking part in the reaction. By lowering the activation energy, the rate of reaction can also be increased. Okay, a catalyst is a substance that increases the rate of the reaction, but remains unchanged at the rate of the reaction. So let's have a look at this graph, and we're going to try and understand what they've just explained to us. The effect of a catalyst on the potential energy versus course of reaction graph. So we have what might look like our regular potential energy versus course of reaction graph, where EA, by the way, this just means activation energy. Okay, where we are shown the activation energy by means of that arrow. Okay, but now we are going to discuss the effect of a catalyst on the specific graph. So the original graph follows this path. Okay, the original graph follows that path. Okay, but now when we add a catalyst, okay, what happens? When we add a catalyst, okay, what happens is the graph starts off with the same reactant. So I'm going to use this gold as well. We start off there and we end there. So we change nothing about the reactants. Okay, I don't know if you see, I just throw the gold line over there. We change nothing about the reactants and we change nothing about the products. But what's different is this little gold dotted line here. The graph no longer goes all the way up to this activated complex. It only goes up to that. It only goes up to this activated complex. So as you can see now, the activation energy, okay, the activation energy of the gold graph is represented by this. Okay, this is with a catalyst, by the way. Okay, so I'm just showing you the effect of a catalyst. So as you can see, the original graph, okay, it starts off with the same amount of reactants, goes up to this activated complex, goes all the way down to the products. However, the graph with a catalyst, so once we add a catalyst, we start off with the same amount of reactants and we go up to a smaller activated complex and then we go to the same product. Okay, so the start and the end doesn't change, but what changes is in the middle. And that is basically, it decreases the activation energy. So if we compare the two activation energies, we have that activation energy and we have that activation energy. And we can clearly see with a catalyst, okay, the activation energy is smaller. And that's really, that's vital to speed up the chemical reaction, because now we no longer need as much energy for the reaction to occur. That's the beauty of a catalyst, okay? It comes in and it speeds up the chemical reaction because now you don't need to reach such a high energy level, okay? So for instance, maybe this was like 300 joules. But here with the catalyst, it was 250 joules, just random numbers. Okay, so now we don't have to reach those 300 joules of energy. We can just reach the 250 and the reaction will occur. Okay, that is the beauty of a catalyst. Okay, so the catalyst comes in, speeds up the chemical reaction without making any changes to the reactants, no products, and without it itself being changed. So the catalyst is not affected. The catalyst does not involve itself in the reaction. Okay, it does not take part in the reaction. Okay, it doesn't change the amount of product we form. Don't have that misconception. It doesn't increase the amount of product we form. No, that's not what the catalyst does. It just takes us from point A to point B faster than without the catalyst. Okay, so we're going from reactants to products. Okay, but with a catalyst, it would be faster. Okay, and as you can see, the gold dotted line, you don't have to go all the way up to that. We don't have to go all the way up to that old energy activated complex. Okay, it has a lower activation energy. Okay, and that's what they define it as actually. A catalyst is a chemical substance that lowers the activation energy required without taking part in the reaction. By lowering the activation energy, the rate of the reaction can also be increased. Okay, important notes there. Okay, and that's it. I think this is just the science clinic notes. Okay, so instead of starting acids and bases, because that would be acids and bases would that it's a lot and it's intricate, right? Let me what I want to do, sorry, let me just find a question quickly and we can attack a question. I think that's a good idea. So take a minute to just breathe, okay, relax, and in like a minute or two, we'll just start up doing a practice question. Okay, cool. So let me just share my screen. And we can have a look at these questions. It's not an intricate section, right? It's quite a simple section. So the questions are not too difficult. Okay, so let's answer these questions. So a few multiple choice and then one regular question. So 1.4, consider the potential energy graph for the hypothetical reaction. 2p gives us p squared. Sorry, not p squared, but p2. Okay, a little subscript of 2. The heat of reaction enthalpy is represented by, okay, so we have different values. We have Z, Y, X, okay. 2P is, as you can see, 2P is the reactants, right, which makes sense to us actually. This is our reactants, and then this is our products. Okay, that makes sense, all right? Now, enthalpy doesn't, it has a set formula, okay? Enthalpy is always calculated by energy of products minus energy of reactants. Okay, energy of products minus energy of reactants. So in this case, we would have the energy of the products being here. Okay, and the energy of the reactants being there. This we can call EP, and this we can call ER, energy of reactants. Okay. And essentially, it's going to be, this is X and that's Y. So it's going to be X minus Y. So correct answer is B. Okay, X minus Y just represents values on the Y-axis for potential energy. Okay, let's look at the next one. 1.5, enthalpy in kilojoules per mole for the reverse of the reaction below is, so we have a reaction, okay, A2 plus B2 gives us 2C, and the delta H is negative 1,200. So remember that delta H is always calculated by EP minus ER, okay? And in this case, the products are here and the reactants are here. So what the reverse reaction is, so if the forward reaction, we have two reactions. We have a forward reaction and we have a reverse reaction, okay? So the forward reaction is the regular one, just like how it's written. Gives us 2C. The reverse reaction would basically mean that you'd swap them around. So the products become the reactants and the reactants become the products. So 2C would give us A2 plus B2. Okay, so initially the forward reaction, this has a delta H of negative 120. I'm not going to put the units. Okay, but that was when we said energy of products minus energy of reactants. Now that changed. The products now have this energy, A2 plus B2. But obviously the value still remained the same, right? So in order to get negative 120, maybe this was maybe this was 50, and then this was 108, no, 170. So when we said 50 minus 170, we got negative 120. It's supposed to be negative. Okay, I'm just giving random values. There could have been anything, any calculation that gives you negative 120. I'm just assuming if this was 50 and that was 170, and we said 50 minus 170, okay, we would have got a negative 120. But now that's flipped around because the A2 plus B2 are now the products, okay, we're going to say 170 minus 50. And that's just going to simply give us positive 120. Okay, I'm going to put this kilojoules per mole. Kilojoules per mole. Okay, so essentially the reverse reaction gives you the negative version of what you currently have. And in this case, it's positive 120. The negative version of negative 120 is positive 120. Okay, so just keep that in mind. Let's go through the next question. Question 6. The diagram below represents the potential energy changes for an endothermic reaction. Okay, we can confirm that that's endo, right? You should always memorize how the graphs look. So the graph here, we know that A would represent energy of the reactants and D would represent energy of the products. Here we can see that the energy of the products is higher than the energy of the reactants. Alternatively, we can see that the energy absorbed is less than the energy released. Sorry, more than the energy released, excuse me. Energy absorbed, more than energy released. So therefore, we know it's endothermic, right? We do know that even without them telling that to us. What will happen to the temperature of the surroundings of the above reaction? Okay, see now they're asking theoretical questions. We know that it's endothermic. What is going to happen to the temperature around the above reaction? The temperature around the above reaction is going to decrease, right? It's in one of our notes, actually. In an endothermic reaction, the temperature around the environment is going to decrease. Look, I'll be honest, if you understand the section, there's no even need to like study the theory because everything just makes sense, okay? Because if it's an endothermic reaction, you know it's going to absorb energy. If a reaction is going to absorb energy from the environment's temperature is going to decrease, okay? Let's just see if I can get the memo to see why they're giving 2 marks. Are they just giving 2 marks for that, or is there something else that they want? Okay, but in the meantime, let's move on to the next question. Which lettered interval or combination of letters on the diagram represents the activation energy of the reverse reaction? Okay, we'll come back to that. Let's just see. This is question number 6. Okay, no, they just give 2 marks for saying that the temperature would decrease of the surroundings. Okay. Okay, which would represent the activation of the reverse energy? Okay, so firstly, let's identify the activation of the forward. The forward reaction can simply be from here to here. Okay, there's nothing. Oh, there is C. C represents that. Okay. Oh, sorry. I'm talking activation energy. Okay, so from reactants all the way to activated complex. From reactants all the way to activated complex, this is the energy of activation initially. Okay, so this is for the forward reaction. Of course, the graph given is for the forward reaction. Now, remember the reverse reaction, all the reverse reaction means, that whatever the products were, those become the reactants. And whatever the reactants were, those become the products. These are the reactants, they become the products now. Okay, and then this reaction takes place like this. Okay, this is for the reverse reaction. Okay, and now essentially if we have to look at this graph, the activation energy would be from here to its activated complex. So from there to there. So essentially this is a bit of a weird arrow, but the arrow represents from here to here. Okay, it's like the energy released. Okay, so in this case, activation energy of the products, and then this would be the activation energy of the, this is the activation energy of the reactants, and this would be the activation energy of the products if we were to do the reverse reaction. So it's actually represented by E, okay, because we can see that this value would correlate there as well. Okay, remember, in the reverse reaction, the products become reactants, the reactants become products. Okay, so this is the distance from where to where. This is the distance from the activated complex to the products, which would, of course, behave as reactants in the reverse action. Okay, is anyone still confused by that? Please let me know, but that's the concept. Which combination would represent the activation energy of the reverse? E. Okay, 6.3. If a catalyst could be used to improve efficiency of the reaction, explain how the catalyst, would affect the potential energy in the reaction. Okay, so for 2 marks, you have to basically give the definition of a catalyst. A catalyst, okay, you would say, how would it affect the potential energy? It would lower the activation energy, okay, by providing an alternative pathway. So that's the official definition of a catalyst. Okay, it will lower the activation energy, okay, by providing an alternate pathway. Okay, let's write that. By providing an alternative pathway, okay, a faster pathway for the reaction to occur. Okay. 6.3.2, redraw the graph in your answer book and indicate the changes of the reaction when using a catalyst in a dotted or dashed line. No thanks, we won't do that. We can simply do it here. We're just going to essentially draw a graph, okay, with a lower activated complex. This would be the graph with a catalyst. Okay, the graph with a catalyst. Using only letters, this is 6.4. Using only letters from the graph above, derive a mathematical formula to calculate the change in the enthalpy for this reaction. Now remember, enthalpy, delta H, is calculated by saying energy of the products minus energy of the reactants. So we just have to look for a letter that represents energy of the products. The letter that represents energy of the products, it's not F, by the way. It is D, because it's the energy from the bottom up to the products. Okay, and then the energy of the reactants is from the bottom up to the reactants. That would be A. So instead of EP minus ER, we're going to say delta H is equal to D minus A. And actually, the letter that represents the enthalpy would be F and B. Okay, because it's between, it's obviously D minus A. So it's from here to here. Okay, cool. So yeah, simple question. I don't think it's too complicated. I hope that everyone understood. If you do have any questions, please let me know. Yeah. Okay. That's it, by the way. That's the end of our lesson. For this topic, we will be starting acids and bases next week, which is good news. Please try and ace this section. They ask really simple questions. The concepts are not difficult. Understand them properly. Okay, if you don't, rewatch the explanation of this graph and try your best to understand it. Okay, I don't think it's too complicated. Okay, and another thing is, okay, the session will be open for at least the next minute to see if anyone has any questions. We are running a bit late, sorry about that, but it will then thereafter end and I'll start the next lesson. But yeah, if you need to leave and you don't want to wait for anyone to ask any questions, you are free to leave. But yeah, if you want to hang around to see if anyone has any questions, or if you have a question yourself, then you can stick around. Okay, we have a question. What does E represent again? E. Okay, so for 6.2, right? So let's just discuss it without discussing 6.2. What does E itself represent? Okay, so firstly, A represents energy of reactants, okay, and D represents energy of products, okay, from the bottom all the way up to those specifically. Then we have from the reactants all the way up to the activated complex, right? That is known as the energy absorbed or the activation energy. Okay, and E from the activated complex all the way to the products, that's known as the energy released. The energy released. So the left pink line highlighted is, sorry, 1 second, let me just inform the students. We're going to be slightly late. Okay, so yes, the one on the left represents the energy. This is all now for the forward reaction, for what's given. Okay, the one on the left represents the energy absorbed, right? To go from reactants to activated complex, energy absorbed. Then to go from the activated complex to the energy of the products, because there's the products, right? That is the energy released. So E in itself represents energy released. Energy absorbed, energy released. Okay, energy released. But what do they ask? They say, which lettered interval or combination of letters on the diagram represents the activation energy of the reverse reaction? Okay, which lettered interval on the diagram represents the activation energy of the reverse reaction, sorry. So remember, we have this always, the one that's given would be for the forward reaction, right? And we discussed what is the difference between a forward and a reverse reaction. A forward reaction is like the regular reaction that takes place, right? From products to reactants. But the reverse reactance is when we take the products and use it as a reactant. And when you take the product and use it as a reactant, you are going to form the reactants, okay, with the previous reactants. So they swap. The reactants become a product and the product become a reactant. So they swap around. Okay, so that can be shown here. Okay, so here what I did was similar graph. I took the energy of the product and made it a reactant energy. I took the energy of the reactant and made it a product energy. Okay, and then the reaction takes place between them. Okay, so this is the reverse reaction. Okay, and then I can see that the energy of activation for this reverse reaction would be the energy from the new reactant to the activated complex. Remember the energy from the new reactant is just the product. The new reactant is the old product. So that energy is represented by E. Okay, the energy from the activated complex to the product, okay, is the same energy that's from the it's the same energy that's from the activated complex to this product being used as a reactant, of course, in the reverse reaction. Okay, so yeah, that's why E represents the activation energy of the reverse reaction. Okay, because again, we just have to use the energy of the product as a reactant and the energy of the reactant as a product, right? These are like new reactant and new product, if you will, because now it's the reverse reaction. Okay, and yes, this value here, oh, actually goes up to there, something like that, right? So the energy of activation for the reverse would be the energy from the reactant to the activated complex. The reactant for the reverse is the product from the forward. And that energy we have, it's represented by E. From activated complex to the old product is the same as from the activated complex. That happens one more time, I might lose my mind. Okay, same from the activated complex to the product being used as a reactant. Okay, does that make sense? Okay, so does it mean when they ask for reverse reaction, we change the graph? Yes, exactly, precisely. Yes, correct. If the forward is endo, the reverse is exo, and vice versa. Right, so let's write that here. I'll write it neatly somewhere before I give them the notes. If forward equals exo, reverse is endo. Okay, and vice versa. That's correct. So therefore, with regards to the graph, if we have a graph that's endo, it would represent the forward reaction. Okay, and its reverse graph would be exo, the opposite. That's correct. Okay, but yeah, let us end it there just because we are late for the next lesson. And if you do have any other questions, feel free to message me, or you can ask them in the next week's session, whatever you're comfortable with. But yeah, thank you guys so much for joining. I will see you guys next week. Please have a good week of school and carry on studying hard. Okay, Jazakallah khair. Assalamu alaikum and goodbye.